Good afternoon. We are pleased to welcome you to the Washington Labs Academy webinar series. We hope you find the next hour or so useful and informative. We have developed our webinar series to deal with some of the technical and administrative issues that our customers face on a day-to-day basis. We recognize that engineering challenges can be complex, and we're always looking for ways to support the technology industry. Before we begin, a few housekeeping details. First, I hope everyone can see the title slide on their computer. A recording of this presentation will be sent to all attendees. A full screen view may be preferred. Your selection at your computer can be done by using the menu panel in the menu on your screen. You'll go to View and then select Full Screen. We do estimate that the main bulk of the presentation will take approximately 1 hour. We welcome your questions. You can submit them to us via email at questions@wll.com. And now, I'd like to introduce our presenter. Greg Zhu is a 6G system engineer at Keysight Technologies working on emerging millimeter wave applications beyond 110 gigahertz. Greg authored Keysight's new white paper, a new sub-Terahertz testbed for 6G research, and was a technical contributor to Keysight's new Engineering the 5G World ebook. Greg wrote the design simulation sections in Agilent Technologies LTE book and has authored numerous articles, presentations, application notes, and white papers, including Keysight's Implementing a Flexible Testbed for 5G Waveform Generations and Analysis. Before joining HP and Agilent, Greg worked on system design for the Deep Space Network at the Jet Propulsion Laboratory, Caltech University. So, without further ado, let's turn our attention to new sub-Terahertz R&D testbed for 6G research with Greg Zhu. Hi, Greg. It is all yours. Please take it away.
Hello, my name is Greg Zhu. I'm a 6G system engineer at Keysight Technologies working on Keysight's Sub-Terahertz testbed for 6G research. Sub-Terahertz frequencies are an active area of 6G research because there's large swaths of contiguous spectrum which could potentially be used to achieve high data throughput rates of 100 gigabit per second or higher. However, there are a lot of unknowns in these Sub-Terahertz frequency bands, and a flexible testbed will be discussed to help explore these unknowns. This new Sub-Terahertz testbed provides flexibility for early 6G research in being able to explore potential candidate 6G waveforms, perform error vector magnitude or EVM measurements with up to 10 gigahertz of occupied bandwidth, explore candidate 6G frame structures with a new VSA flex frame capability, and perform channel sounding measurements at D and G band. In addition, the Sub-Terahertz testbed receiver can be customized with custom FPGA HDL code for user-defined real-time baseband processing. Here's the agenda for today's presentation. We'll start with discussing some considerations for Sub-Terahertz system performance and show some simulation case studies to highlight some of the key considerations. Next, we'll apply this to a new Sub-Terahertz testbed for 6G research and show what type of residual EVM is achievable in the 140 gigahertz frequency band with modulation occupied bandwidths of up to 10 gigahertz. Now, getting to 100 gigabit per second will likely involve high symbol rates, high order modulation with wide modulation bandwidths at Sub-Terahertz frequencies, which in turn will result in low signal noise ratio or SNR. It can be difficult to demodulate signals in a low SNR environment, so we'll show and demonstrate recent enhancements made to the testbed's VSA software to enable more robust EVM measurements to be performed on low SNR signals. Sub-Terahertz frequency bands are largely unexplored, so we'll discuss some D-band channel sounding work that was performed with the testbed to sound the channel and explore channel propagation characteristics. Lastly, we'll discuss and demonstrate an example of an FPGA customization of the Sub-Terahertz testbed receiver with an implementation of a real-time adaptive equalizer and bit error rate measurements. The customization approach is flexible, enabling the testbed to be customized by the user with FPGA HDL code. Finally, we'll conclude with a summary and some additional resources. New regions of spectrum offer the potential of using these frequency bands for breakthrough high data throughput applications. However, there are four key considerations in optimizing the performance of sub-terahertz systems operating over these wide or extreme bandwidths. Optimizing signal noise ratio, or SNR, minimizing phase noise, addressing linear and nonlinear impairments, and making a waveform selection. Optimizing SNR is an important consideration to achieve the best EVM performance. Regarding the S in SNR, on one hand, maximizing signal power helps to achieve higher SNR. On the other hand, reducing the signal power is necessary to avoid compressing any components in the signal chain given some statistical peak to average characteristic of the complex waveform. Regarding the N in SNR, the noise contributions for SNR can be problematic for wideband applications because the noise power is integrated over such wide signal bandwidths. So for example, a 6G 10 gigahertz bandwidth signal would have 1,000 times more integrated noise than a 10 megahertz LTE signal. Regarding the R in SNR, the signal noise ratio, or SNR, is effectively squeezed both on the high end and the low end. This is a key consideration in moving to extreme bandwidth test systems, and the SNR can often translate into effectively what type of residual EVM is achievable. Phase noise is critical, particularly for these high-frequency systems due to the 20 log n degradation of LO phase noise. To illustrate this, Keysight's path wave system design, or system view, is used to simulate the effects of LO phase noise on a hypothetical sub-terahertz upconverter design. The simulation case study uses a simple upconverter design with a modulation IF signal source set to a center frequency of 6 GHz. The modulation order can be set to QPSK, 16 QAM, or 64 QAM, and the symbol rate is set at 8.8 GHz with a root raised cosine filter alpha of 0.22. The modulated IF is upconverted to 144 GHz using a mixer with a low side LO. The LO source frequency is set to 23 GHz, followed by a ×6 multiplier. So the mixer LO frequency is 138 GHz. 138 GHz plus 6 GHz IF yields an upconverted frequency of 144 GHz. Here the LO phase noise is specified in terms of dBc per hertz at different frequency offsets, so the phase noise is modeled with frequency offsets greater than 100 kHz. A vector signal analyzer VSA sync sits at the upconverter output. This VSA sync will use the PathWave 89600 VSA software to post-process and analyze simulation results. However, the same VSA software works with Keysight signal analyzers, oscilloscopes, and digitizers if you're performing hardware measurements. The simulation results for this first scenario are shown on the left. On the lower left of the VSA display, we see the signal centered at 144 GHz with approximately 10 GHz of occupied bandwidth. On the upper left, we see the 16 QAM constellation. If we zoom into one of the constellation states, circled in white, we see some minimal dispersion as a result of the LO phase noise, which corresponds to the 1.56% EVM shown on the summary. A second scenario, shown on the right, increases the phase noise by 10 dBc per hertz at the higher frequency offsets. The rotation of the constellation states and increased dispersion is a result of the increased phase noise, and EVM increases to 4.07%. When upconverting, removing undesired image products, LO feed-through, out-of-band spurious products, and emissions typically requires filters. Filters, as well as other components in the system, such as mixers and amplifiers, can introduce linear amplitude and phase error over these extreme bandwidths. So an adaptive equalizer can help to mitigate some of the linear amplitude and phase error, similar to what might be implemented in a baseband receiver. To illustrate this, a bandpass filter centered at 144 GHz and a power amplifier, or PA, are added to the up converter design. The amplifier has an output 1 dB compression point specified, and an output third order intercept point, or TOI, is specified for the mixer to model its nonlinear characteristics. The simulation results on the left VSA display shows EVM without the adaptive equalizer enabled. The EVM is 15.99%, and the associated dispersion is seen on the constellation states. It's difficult to determine, however, if it's the linear amplitude and phase error from the bandpass filter or the nonlinear distortion from the PA or mixer that is causing the distortion. To gain more insight into the error contributors, the simulation results on the right show EVM with the adaptive equalizer enabled. EVM is better than it was without equalization, but it has increased to 4.57% compared to the scenario without the bandpass filter and PA because of the nonlinear impairments from the mixer and the PA. The adaptive equalizer can't correct for nonlinear impairments, so it's removing only the linear amplitude and phase errors from the bandpass filter. Nonlinear impairments remain and have increased the EVM result. After the adaptive equalizer is run, a diagonal pattern shows up in the constellation state. The pattern is a result of gain compression that is now present on the signal, and it shows how the adaptive equalizer corrects for linear impairments, but it doesn't correct for nonlinear impairments. Next, we'll discuss a new sub-Terahertz testbed for 6G research and show what type of residual EVM is achievable in the 140 GHz frequency band with modulation occupied bandwidths of up to 10 GHz. This shows Keysight's new extreme bandwidth R&D sub-Terahertz testbed for 6G research. Similar to the previous setup shown, an M8195 AWG generates the wideband and extreme bandwidth modulated IF signals. Typically, an IF center frequency of anywhere from 4 to 6 GHz is used to provide an IF frequency that is high enough to allow for filtering of the undesired image product after upconversion to the sub-Terahertz frequency band, but low enough to achieve optimal EVM performance because of the oversampling processing gain with the M8195A's sampling rate. VDI compact D or G band upconverters upconvert the 4 to 6 GHz IF from the M8195 to the desired sub-Terahertz frequency band. These compact VDI upconverters use a ×6 multiplication factor for the LO frequency. On the receive side, the signal is downconverted with a compact VDI downconverter back down to a 4 to 6 GHz IF, then digitized with either a 33 GHz UXR multi-channel high-performance oscilloscope or an M8131A multi-channel AXI streaming digitizer. We had discussed the importance of low phase noise. Here, a 67 GHz PSG signal generator with option U and Y provides a low phase noise LO for the VDI converters. Both the M8195A AWG and the UXR oscilloscope are multi-channel to enable MIMO research. Single carrier QAM measurements were performed at D-band at 144 GHz center frequency with varying modulation bandwidths. These were conducted measurements, waveguide to waveguide, without horn antennas. Since 6G waveforms are not defined, 802.11ay waveforms were used as an initial test case and as an example of an emerging millimeter wave wideband standard with optional bandwidths up to 8.64 GHz of bandwidth. Software was used to generate the 802.11ay 4 GHz IF signal with the AWG. The signal was then upconverted to 144 GHz with the VDI upconverter. After the signal was downconverted from 144 GHz back down to a 4 GHz IF with the VDI downconverter, the UXR oscilloscope digitized the IF and software was used to demodulate it. Here we're showing measurements for an 802.11ay two-bonded channel configuration, or CB2, signal centered at 144 GHz with 4.32 GHz of channel bandwidth. These measurements were performed for a 16 QAM MCS12 signal, but higher order 64 QAM MCS20 signals have also performed similarly. No calibration was performed for these measurements. The same test setup was used to perform measurements for an 802.11ay 4-bonded channel configuration, or CB4, signals centered at 144 GHz with 8.64 GHz of channel bandwidth. The CB4 test case used a higher frequency 5 GHz IF to make filtering of the undesired image easier. As expected, there was some EVM degradation relative to the CB2 case because the modulation bandwidth doubles, increasing the integrated noise power within the signal bandwidth. In addition, there's more linear amplitude and phase variation as the signal bandwidth increases. Again, no calibration was performed for these measurements. And now I'd like to show you a brief OTA demo of the testbed.
Hello, my name is Greg Jew with Keysight Technologies. Today we'd like to show a new sub-terahertz R&D testbed for 6G research. The testbed consists of an M8195A arbitrary waveform generator, or AWG. This is used to produce a wideband IF. In this case, the wideband IF is centered at 6 GHz with a modulation occupied bandwidth of approximately 10 GHz. The 6 GHz IF is run into a VDI compact upconverter. This is a G-band upconverter covering a frequency range of 140 to 220 GHz. The LO is produced by a PSG vector signal generator. This is set at 23 GHz. The 23 GHz LO is input into the VDI upconverter where it's multiplied by a factor of 6 up to 138 GHz. So we have a 6 GHz IF coming in. It's being mixed with 138 GHz LO to produce an upconverted product at 144 GHz. So we have 144 GHz coming out of the VDI upconverter. It's amplified and filtered using a VDI amplifier and filter, and then transmitted over the air with a rectangular horn antenna. The signal is then picked up by a horn antenna on the receive side. It is downconverted back down to an IF using a VDI compact downconverter. The horn antenna spacing in this case is roughly 14 inches or approximately 35 centimeters. The IF is then run into an M8131A digitizer. The signal is digitized and then it's analyzed and demodulated using Keysight's vector signal analysis software. So here we're showing the demodulation results. We have the 128 QAM constellation, so it's a very high order modulation. And you can see that the waveform quality is very good, despite the fact that this is centered at 144 GHz, extremely wide bandwidth, and it's being transmitted over the air. To show you how wide the spectrum is, we're also measuring the spectrum, which is a slower trace. And in the blue shaded region, we're calculating or measuring the occupied bandwidth, which is roughly 10.7 gigahertz, so extremely wide bandwidth. Now to show you that this is a live demo, if I insert this between the horn antennas, we can see that the constellation and the spectrum kind of disperse. The waveform is being both generated and analyzed with software using this testbed. So the testbed is inherently very flexible in being able to prototype different candidate waveforms for 6G. In addition, the testbed is inherently multi-channel. Both the M8195 and the M8131 are multi-channel instruments. So the number of channels can be scaled up for MIMO research. So for more information on this testbed, please contact Keysight Technologies. Thank you for your time today.
As we had discussed, low SNR is a challenge with these wide bandwidth, high frequency signals. So we'll next discuss some new capability with the testbed's VSA software on improved demodulation robustness for wide bandwidth, low SNR signals. Current 6G research is focused on the sub-Terahertz region from 100 to 300 GHz, which is a frequency range of interest for 6G. Sub-Terahertz frequency bands offer much wider contiguous swaths of spectrum compared to traditional millimeter wave frequency bands, so sub-Terahertz systems can potentially achieve much higher capacity. However, achieving robust performance in wide bandwidth, high frequency systems in low SNR scenarios is very challenging. Wide bandwidth sub-Terahertz system performance will be impacted by RF impairments and reduced power amplifier efficiency, so both linear and nonlinear RF impairments must be compensated. This figure shows the flexibility for different generations of cellular communications. Transmitter and receiver flexibility generally increases with newer generations, with 5G being the latest. The main flexibility of 5G, the most recent standard, is the introduction of a numerology concept where different configurations are used to address varying requirements. 6G is expected to have enhanced flexibility options relative to 5G, but this presents additional challenges for 6G systems. A flexible waveform system is required to overcome flexibility challenges on the PHY and MAC layers, and new techniques should be developed to allow enhanced flexibility. A new vector signal analysis, or VSA capability, is introduced to provide enhanced waveform measurement flexibility with Keysight 6G Testbed. This new capability allows multiple waveforms to be used in the same frame to provide enhanced flexibility such as preamble, pilot, and data payloads. Preamble and pilot-aided synchronization and channel estimation are used to provide robust demodulation performance in low SNR environments. Both periodic and burst-type signals can be analyzed with FlexFrame by defining them in the frame definition panel. The signal type can be selected in the frame configuration along with the symbol rate and the frame length. If the signal type is burst, then the auto mode can be selected to automatically detect the frame boundaries. The user can flexibly design each allocation after adding them in frame parts using configuration in the frame definition panel. The length and location of each allocation in the frame can be defined in location. If the allocation is repeated in the frame, then the user doesn't need to define the allocation part each time. Instead, a repetition structure can be defined as a repeat pattern in the frame definition panel. Another great feature of FlexFrame measurement is the measurement control panel. To configure a certain component carrier, the user should select it here. If all is selected, common configurations for all component carriers can be configured. In this example, there's only one component carrier. From overall allocation control, the user can flexibly select groups of allocations for channel estimation and synchronization. Moreover, the allocation that is preferred to be included in EVM calculations can also be chosen by enabling the corresponding checkbox. Equalization and synchronization section allows the user to choose synchronization and channel estimation sources. For example, if the user wants to use the preamble for synchronization and the pilot for channel estimation, the corresponding selection can be done here. Two equalization methods are supported by FlexFrame, which are zero forcing and least mean squares. This can be selected in the equalization mode. In zero forcing, the channel equalization is done in the frequency domain by taking the inverse of the frequency response. In least mean squares, equalization is done in the time domain to minimize EVM. Now let's take a look at a case study. This picture shows a picture of the 6G testbed setup. An M8195A arbitrary waveform generator, or AWG, generates the wideband IF. The IF center frequency is 6 GHz, and with the 8.8 GHz symbol rate and root raised cosine filter alpha, the occupied bandwidth is approximately 10 GHz. The M8195A IF is upconverted to 144 GHz with a compact Virginia Diodes Incorporated VDI G-band upconverter. It's then bandpass filtered with a VDI waveguide filter, and then downconverted back down to 6 GHz IF using the compact VDI G-band downconverter. A PSG with the low phase noise option, UNY, provides the LO for both the upconverter and the downconverter. The downconverted IF is digitized with an M8131A digitizer for analysis with the VSA software using the new FlexFrame demodulation capability. This shows the attempted demodulation of a 256 QAM signal with a 10 GHz occupied bandwidth at 144 GHz without VSA FlexFrame. In contrast, this shows a successful demodulation of the 256 QAM signal with 10 GHz occupied bandwidth at 144 GHz using VSA FlexFrame on the 6G testbed. FlexFrame can analyze very high order modulation formats at sub-terahertz frequencies with wide bandwidths robustly in low SNR environments using Preamble and pilot-aided synchronization and channel estimation. The testbed can also be used for channel sounding, so next we'll discuss some recent channel sounding work that was done at D-band. Okay, let's first start with the basics. Channel sounding is the process of measuring the response of a channel to an impulse. When you know this information, assuming that your channel is linear and time invariant, you can predict what the response would be to any signal that you put into the channel. This is because the signal can be expressed as a linear combination of impulses. You simply compute the channel response to each impulse in your signal and then add the responses together to get the total response to your signal, a process also known as convolution. Note that a channel can be anything in between the output of the channel sounding signal and the input to the analysis hardware. So to summarize, the channel sounding procedure is send a known signal into the channel, capture the signal after the channel, and then compute the channel response by comparing the sent signal to the received signal. Let's take a look at one particular channel in a top-down view. This channel is a free space environment that contains several reflective objects. If we send a signal into this environment using an antenna, in this case using Keysight's custom modulation signal studio software connected to an arbitrary waveform generator, the signal will disperse and reflect off the objects in the channel. The power that makes it to the receive antenna can then be captured by the acquisition hardware and analyzed by the channel sounding software in the PathWave 89600 VSA software. So let's stop for a minute and ask why. Why do people need to measure channels? One common use case is a network measurement. Although a network analyzer might be a more appropriate choice here, you can measure the S21 frequency response of a two-port device with channel sounding. Another use case is end-to-end calibration. Let's say, for example, you have a signal generator, you want to measure the EVM of a device with a particular modulation, but you also want to remove the effects of the test fixture from the measurement results. Lastly, an active area of 6G research are new sub-terahertz bands such as 100 to 300 gigahertz. These are of interest for 6G research because wide modulation bandwidths could be used to achieve high data throughput rates of 100 gigabit per second or higher. However, these frequency bands are largely unexplored, relatively new, and uncharacterized, so channel sounding may be needed as part of early 6G research. For example, what does a channel inside a building look like when you transmit inside the building, or what is the difference between wood and concrete buildings? These are the types of questions that can be answered by channel sounding. Now let's show an actual channel sounding measurement with the 6G testbed. Here's our channel. We have two reflectors and an RF chamber. The reflectors are made of boards covered with aluminum foil and mounted on tripods. Then we have our transmitter and receiver on a table at the back of the chamber. The top-down view is shown to the right. The black rectangle represents the table, and the orange boxes represent the instruments on the table. There are two signal converters, each with a horn antenna. The two reflectors are placed roughly 1 meter and 2 meters away from the transmit and receive antennas. When the sounding signal is transmitted, the receive antenna will see two main reflections of the transmitted signal, separated in time. Here's a close-up of the 6G testbed configured for channel sounding. Now previously we had discussed the testbed being used to perform EVM measurements at D and G band, but here we're using the same hardware to perform channel sounding. On the left, we have the 89600 VSA software and Signal Studio software running on a controller PC in the AXIE chassis. The Signal Studio software sends the channel sounding signal to the M8195A AWG, which is also in the AXIE chassis. And the 89600 VSA software captures the data from the UXR oscilloscope on the right side of the table. The signal from the M8195A AWG transmitted at a symbol rate of 4 gigasymbol per second at a center frequency of 6 gigahertz. This IF signal is then upconverted by the VDI upconverter to a center frequency of 144 gigahertz and transmitted using a horn antenna with a nominal beam width of roughly 9 to 10 degrees. The PSG behind the converters provides the LO, local oscillator, for both the converters through a splitter. The LO could have been provided by separate instruments, but since the transmitter and receiver were closely spaced, in this example, we connected it this way for convenience. The downconverter then downconverts the signal back down to a 6 gigahertz IF, and the signal is captured by the oscilloscope. Now let's take a look at the measurement results. On the left side, we see the basic spectrum and some signal metrics. The spectrum is useful to verify that your signal is present, and the metrics give you a sense for whether or not there's any impairments that might affect the measurement of the channel. On the right side, we have the frequency and time domain versions of the channel response. The trace that's of most interest in this example is the impulse response. This trace shows the various reflections in the channel. This includes their location and time, their amplitude, and if you were to select a different trace format, their phase relative to the measurement carrier. If the channel were purely a flat channel, you would only see one path. Depending on the physical arrangement of the transmitter and receiver, you can interpret the paths that you see in the impulse response. If the transmitter and receiver were on either end of the room, you can interpret the highest path as the direct line of sight path and the other paths as reflections off the walls of the room. In our example, both the transmitter and receiver are located in the same plane and are pointed at objects in the room. The highest path in the impulse response may not be the first reflector, depending on how absorptive the reflector is relative to the others. But in this case, both reflectors are made of the same materials, so the amplitude differences can probably be attributed to free space loss or to slight beam misalignment. In this impulse response, we can interpret the first peak as the closer reflector and the second highest peak as the second reflector. Electromagnetic waves travel at approximately 300 million meters per second in air. Inverting this value gives us a value of 3.33 nanoseconds per meter traveled. Since the path difference between the two reflectors is 2 meters, we should see an approximate 6.7 nanosecond between the two paths. Let's make a rough measurement using delta markers. First, place a marker on the peak. Then choose 0 delta and add a second marker at the same location. Now move the marker to the second peak. We can see that the time difference is about 7 nanoseconds, which is close to the value we would expect from physics. The other smaller peaks are probably reflections off the instruments and walls of the room. As the signal continues to bounce around the room, the power decreases and you can see a gradual decay of the power over time. If we look at the main peak, we can see that it is about 45 dB above the noise floor. Can we do better? Some of the noise can assume to be Gaussian and as such uncorrelated across time. This means that we can average multiple channel response measurements and the uncorrelated part of the noise, if we do vector averaging, will average towards 0. There are two ways to do this in the channel sounding measurement. One is to increase the number of repeats parameter. This will acquire a longer time record and average repetitions of the impulse responses together. This method of averaging is useful to dig the signal out of the noise when the measurement is having trouble synchronizing. However, the measurement will update slower and be more sensitive to symbol clock error. The alternative is to enable VSA measurement averaging. We've selected the exponential version so that the average keeps being updated after the count has been reached. There's enough data in this recording for about 500 averages. The noise floor decreases quickly at first, then slows down. Eventually you'll reach a limit. This is due in part to the residual frequency and symbol clock errors in the measurement, which prevent the sounding signal from modeling an ideal impulse and instead being an impulse with some very low amplitude side lobes. However, we see that the noise floor is about 70 dB below the main peak, which is an improvement of about 25 dB. One last thing to mention is that this channel sounding solution supports multiple receive channels. This allows you to measure the relative differences between channel responses. This could be antennas with different polarizations, or antennas pointed in different directions, or other scenarios. Next, we'll discuss some FPGA customization work that was done with the 6G testbed receiver. The FPGA implementation will show a real-time equalizer and bit rate being performed on 140 GHz over-the-air or OTA transmission. But please keep in mind that the approach is flexible and could be used to customize the testbed receiver for other implementations. 6G baseband signal processing leads to several industry challenges. Sub-Terahertz 6G applications may require very wide modulation bandwidths to achieve 100 gigabit per second data throughput. These wide modulation bandwidths require high sample rates, and these high sample rates will quickly consume baseband resources like available FPGA fabric. Given these industry challenges, we wanted to create a proof of concept FPGA implementation for the 6G testbed receiver. We selected an adaptive equalizer as a proof of concept example. Here are the objectives for the channel equalizer FPGA implementation. The first objective is to create a proof of concept to customize Keysight's 6G testbed receiver using VDI D-band or G-band converters, the M8131A digitizer, the M8132A FPGA DSP module, and Pathwave FPGA. Another objective is to implement a real-time adaptive equalizer example. The goal here is to show an example of customizing Keysight's 6G testbed receiver. By creating this equalizer example, we also want to demonstrate the ability to use Keysight hardware to equalize a 10 GHz occupied bandwidth signal at a center frequency of 144 GHz. There were several key technical challenges encountered when creating the testbed receiver equalizer demo. The first technical challenge is the extremely wide bandwidth signal on the order of 10 GHz of bandwidth. This leads to the second technical challenge where large signal bandwidths will require extremely high digitizer sampling rates. As the sampling rate increases, the hardware resources needed to handle the high sample rates increases considerably. For these applications, the sample rate could be considerably higher than the FPGA clock frequency. For example, if the sample rate is 32 gigasample per second for the digitizer and the FPGA clock frequency is 400 megahertz, then in order to process 32 gigasample per second data using an FPGA with a 400 megahertz clock frequency, 80 samples must be processed during a single FPGA clock cycle. When processing multiple samples at once, all of the FPGA algorithms are required to be parallelized. For example, to design an FIR filter that processes 80 parallel samples per clock cycle requires 80 parallel FIR filters. If a single FIR filter requires 20 multipliers, the bank of parallel FIR filters needed to process 80 parallel samples per clock will require 1,600 multipliers. This quickly consumes large amounts of FPGA resources. Another key technical challenge is that as the number of FPGA resources used and the design complexity increases, it becomes harder to meet FPGA timing constraints. It takes many FPGA build iterations to try different logic pipelining and logic optimizations to get a complex FPGA design to meet timing. An FPGA build can take 2 or 3 hours or more to complete, so the design iteration cycle can take some time. An M8132A DSP module was added to the 6G testbed for the FPGA customization. The M8132A DSP module has two user-accessible Xilinx Vertex UltraScale Plus VU9P FPGAs connected to the ODI or optical data interface ports used to stream data between other modules. In this example, the M8132A DSP module receives the digitized data from the M8131A digitizer module for real-time processing. Here is a high-level block diagram of the system. Keysight's path wave system design, formerly known as System View, is used to generate a transmit QPSK waveform. This waveform is loaded into the memory of the M8195A arbitrary waveform generator module. The M8195A AWG transmits the waveform at an IF of 6 GHz. A VDI upconverts a 6 GHz IF to 144 GHz and transmits the 144 GHz signal out of a horn antenna and over the RF channel. The transmit waveform is then downconverted back down to an IF of 6 GHz with a VDI downconverter, and then digitized with an M8131A digitizer. The digitized waveform data is then sent over an optical connection to the M8132A DSP processing module. The M8132A has two FPGAs, and the channel equalizer is implemented in both FPGAs. The equalizer results are then sent to a host PC and displayed using Keysight's test automation software. And now I'd like to show you a brief OTA demo of the testbed receiver FPGA customization.
Hello, my name is Greg Ju with Keysight Technologies. I'm a system engineer working on Keysight's 6G testbed. Sub-Terahertz frequencies are of interest for 6G. In fact, it's a very active area of research. And the reason is sub-Terahertz frequencies offer large, contiguous swaths of spectrum that could potentially be used to help achieve high data throughputs of 100 gigabit per second to a terabit per second. However, these sub-Terahertz frequency bands are largely unexplored. So 6G researchers are going to want to do things like channel sounding to understand propagation characteristics, and eventually receivers will have sophisticated baseband algorithms to be able to address channel impairments. So today we'd like to show Keysight's Sub-Terahertz testbed for 6G research. Now we've shown this testbed before for wideband EVM measurements, and it can also be used for channel sounding. But today we'd like to show how the Keysight Sub-Terahertz testbed receiver can be customized with the user HDL code. Specifically, we're going to show a customization example, which is an FPGA real-time adaptive equalizer implementation. So the test setup consists of an M8195A AWG. This is used to produce a wideband IF, which is run into a Virginia Diodes Incorporated or VDI upconverter. The signal is upconverted to 144 gigahertz. It's then amplified, filtered, and transmitted over the air with this horn antenna. The signal is received with this horn antenna, downconverted back down to an IF, and the IF is run into the M8131A digitizer. Now you'll notice that there were optical links connecting the digitizer to this M8132A DSP module, and this is where the FPGA customization is going to occur. So with this, I'd like to introduce my colleague Eric, and he's going to take us through the FPGA implementation and do a live demo.
Thanks, Greg. Hi, my name is Eric Wilson, and I am an FPGA engineer with Keysight Technologies, and I will be walking you through the system-level block diagram of the 6G channel equalizer solution. So once the 144 gigahertz transmit signal is received, it is down converted to an IF of 6 gigahertz and digitized with the M8131A digitizer. The digitized data is sent over an optical connection to the M8132A, a DSP processing module. This module has two FPGAs in it, and our channel equalizer is implemented in both FPGAs. The digitized data is first down converted to baseband with an LO block, and then we trigger on the beginning of the waveform. The waveform data is oversampled by a factor of 4, and the channel equalizer runs at the symbol rate. So we need to use a root raised cosine decimating filter to decimate down to the symbol rate. Once we are down at the symbol rate, the data is sent across an inter-FPGA link to the second FPGA with the channel equalizer. The channel equalizer will equalize the IQ symbols, and we send the equalized IQ symbols up to the host PC. We also send the equalized IQ symbols through a bit error rate block that will calculate the bit error rate results, and we send that up to the host PC along with the channel equalizer coefficients. On the PC side, we use Keysight test automation software to plot and visualize the results, and we were able to plot the IQ constellation, bit error rate versus time, and channel equalizer frequency response. And now I'll do a live demo of the 6G system running. On the screen on the top trace we have the equalizer frequency response. On the lower left trace we have the bit error rate versus time. On the lower right trace we have the equalized IQ symbols showing a transmit waveform with an 8 GHz symbol rate and an occupied bandwidth of 10 GHz. I'll now demonstrate blocking the RF channel with an object, and we will see that the bit error rate goes up to 50% and the IQ constellation plot becomes distorted. When I remove the object and the channel returns to normal, you'll see that the bit error rate goes back down and the IQ constellation plot returns to normal. I'll demonstrate this again by taking the object and placing it in the RF path, and we can see the bit error rate increases and our IQ symbol plot is distorted. And once again, when I remove the object, the channel returns to normal. Thank you for your time today. For more information, please contact Keysight Technologies.
Now let's summarize and reference some additional resources. We hope you found this work interesting and informative. There are some additional resources that I'll cover next, but to summarize, we covered a flexible new sub-Terahertz testbed for 6G research. It provides flexibility in evaluating candidate 6G waveforms, performing EVM measurements with up to 10 GHz of channel bandwidth, a new VSA flex frame demodulation capability for more robust EVM measurements in low SNR environments, being able to perform channel sounding measurements, and finally, flexibility in being able to perform FPGA customization of the Sub-Terahertz testbed receiver. There's also 2 new white papers available for additional information. A Sub-Terahertz testbed white paper is available along with a demo video shown. These are posted at keysight.com/find/6G. The most recent work with the channel sounding and FPGA customization has also been released in a second white paper. This along with demo videos are posted at keysight.com/find/6G. We hope you found this presentation both interesting and informative. We'd like to thank you for your time today.